Bueno, la otra es que es USB, no es
Okay, thanks for your hospitality. As you know, I'm in the security department, and tomorrow we'll have a presentation on language evolution. If anybody is interested, it's tomorrow morning at 10:30. And Bernat will be one of the members of the committee, so given that he will come and completed his PhD last summer, we thought it would be interesting for you to know his work. He's been working in the group of Ricard Soler in Barcelona, which rings a bell in case. And I think, well, it's an opportunity also for Bernat to present his work. Highly distinguished.
Well, thank you, and thank you, Danny, for providing me the opportunity to show the work I developed last years, part of the work I developed last years, and thank you to all the people at the IFISC, because it's an interesting center where to show this kind of achievements. Well, I will talk about scaling in complex systems. I'm sure that many of you, when you saw the title, said, again, we are going to talk about scaling in complex systems. And moreover, if you know more or less what I did in this work, I think in this field of research, maybe the papers to which I'm most proud about are related to Zipf's law. And again, we are going to talk about Zipf's law. So I will try you to convince that what I'm going to show you is slightly different, because the effort we made in the past, developing the theory I will show you now, was mainly devoted to provide a fundamental explanation for the emergence of scaling in many different systems, instead of looking for a particular explanation of a particular mechanism in a specific system. So, first I will invite you to do a simple experiment showing how present is the scaling behavior in our lives. Then we are going to show how we can mathematically characterize the systems we are talking about, which are astonishingly different. Then we are going to see that the mathematical characterization, which is very general, we provided, has the only solution. So it generates a problem whose only solution is the scaling behavior known as Zipf law. Then we have an epilogue in which I will show that the formalism we developed here fits perfectly with Zipf's hypothesis, specifically the least effort hypothesis, by which the linguist George Kingsley Zipf wanted to explain the emergence of this behavior in human language. And in the end, I will present the main conclusions, and I will comment the works that inspired this presentation, and some interesting works if you want to follow in this direction. So, simple experiment. The first thing we have to do is to take one of your favorite books. I choose this one, which is one of my favorite books. Then try to find the electronic version. Then we have to manage the text in a more or less appropriate way, in such a way that what we want to obtain is a list of words ordered by its rank of appearance. So in the end, with a short list of Linux commands, what we are going to have is a list, or what we want to have is a list of all the words appearing in the text ordered by its rank of appearance. Then you can plot what you obtained in your phone program representation we don't see anything special here. But if we plot it in a log scale, what we see is a more or less well-shaped power law with an exponent close to 1. This scaling pattern is known as Zipf's law. And it's due to the fact that this scaling pattern was popularized by the linguist George Zipf. However, this pattern was observed before in the distribution of city sizes and many other systems. But in the case of complex codes, Zipf had an intuition. It was, okay, when we try to speak, what we do is to try to use the minimum number of words necessary to refer to a set of events. However, if I am listening to a discourse, what I want is the vocabulary to be as specific as possible in order to avoid the effort of reconstructing what the speaker is saying. So there is a tension in the communication which is solved by balancing these efforts. However, many real systems, as I told you, follow probability distributions close to Zipf's law. For example, the distribution of city sizes. For example, the distribution of money in a society. For example, the family names, the size of companies, and many other systems. So we can be more or less sure that Zipf's law is one of the most, or even maybe the most widespread scaling behavior. And a plethora of papers in which Zipf's law behavior is reported for a different system, or in which they try to provide an explanation for a singular system showing this scaling behavior, or trying, like this paper, trying to find a general solution or general explanation why this scaling behavior is emerging. So the topic is so important that even in non-scientific journals, the problem has been set up as one of the problems that sociology or whatever, because it goes beyond physics, has to solve. I refer to this column of Stephen Sturgett's in New York Times. So, such a scaling behavior is so common that if you want to have an explanation to account for its emergence, we have to go beyond specific systems. So we need a fundamental explanation not linked to a specific model. Okay, there is a quote of Herbert Simon saying that, I don't remember exactly what he referred, but he said that I don't expect any relation between all the systems exhibiting scaling behavior, but a few mathematical properties, which in this case were related to the vision he had of urban problems to solve or to explain this kind of behaviors. Following this idea, but in a different direction, what we are going to do is try to have an abstract characterization of the main properties shared by all the systems exhibiting this kind of behavior. And it's dangerous because the differences are so different that maybe we are going to be so generic that we don't end in anything interesting. But we are going to try. What we are going to do is to define or to describe a very general class of complex systems which grow in time, so they change their nature, they have new states, whose complexity grows while the system grows, and it can do it undoubtedly. We are talking about systems which are not ordered, but systems which are not completely random, and systems that are subject to path dependency. This is a very important point. These systems are not created by scratch, ex nihilo. These systems, generally, we can report his historical trajectory by saying there was a seed and the seed grew. So, path dependency and evolution are very important in order to understand these kind of systems. So, how can we do it? Well, breaking the problem first. First, we are going to talk about these three general features, and then we are going to talk about evolution. The most general way we can characterize a complex system, or one of the most general ways we can characterize a complex system, is through Kolmogorov complexity, and it's a statistical correlate, which is entropy. This is Kolmogorov and this is Shannon. Kolmogorov complexity is based on a computational computation theoretic framework, and Shannon entropy is based on probabilistic framework. But as we will see, these two quantities are related. So, what is Kolmogorov complexity? Kolmogorov complexity is the minimal amount of bits of the size in bits of the minimal problem, which, when we apply it to a universal Turing machine, this machine is able to completely describe this object. So it's a non-computable measure, and it was defined at the same time, it seems, by three researchers, Kolmogorov, Chaitin, and Solomonov. And one of the aims to describe this, or to define this quantity, was that it provides the exact or the rigorous definition for random system, which means that the system is random if the sequence of observations are the minimal description of the system. So we cannot find any irregularity. So if the length of the sequence of observations we have cannot be compressed in any way, then the system is completely random. Moreover, it can be shown, and it's called the Bernat's theory, that Kolmogorov complexity, if the system accepts a statistical description, is equal to its entropy plus a term, a correct term, which is order 1, so it's not a problem for a statistical physicist. So, we are going to put in specific concepts what we intuitively described at the beginning. So, our system is growing kind. So, the sequence describing the system growing time. The complexity of the system grows as the system grows, and it does so unboundedly. So, the Kolmogorov complexity grows, and due to internal constraints, we are going to be always able to overcome any threshold of complexity. Of course, many external events can break this condition, but it's not internal, so we are not worried about it. And in the end, if the system is not ordered and is not completely random, what it happens is that the system can be compressed. And we assume that it can be compressed in a linear way, which means that the sequence of events can be coded in a smaller sequence, but proportional to, or in a linear relation to the length of the system, to the size of the system. So it's a very abstract characterization.
Will you do some justification of the last assumption?
The last assumption. It
seems to me very strong.
What is very strong?
I mean, why it should be that for any time the complexity of something should be proportional to its length?
Well,
I foresee no reason for that.
Yeah, I can understand you. Actually, what we are saying here is that we don't want. Okay, so let me explain. So this condition means that complexity is unbounded. Okay.
Mm-hmm.
So this condition means something stronger, which says while the length of the object, so the object in this case, increases, then so does the Kolmogorov complexity in a linear relation with it. Yeah? So you feel this is very strong. So if I say that Kolmogorov complexity grows, it's okay. That's a good question. So all the results I will provide to you, I am pretty sure that hold by removing this condition. But it has not been published. So for me, this assumption is at some point is strong, but at some point, since I relax completely between the open interval being 0 or 1, 0 is nothing, it's like something which is perfectly ordered, and 1 would be the complete disorder, then I feel safe because I'm saying, okay, I am only imposing a slight condition. Yeah?
So you are making you will prove something for this in this method.
Yeah, but I want to stress that it seems really restrictive, but it isn't. Because you can put this mu like 0.00001, or you can put this mu like 0.9999, and the result still holds. So we should not be scared by this linear dependence. So thanks to this equality, we can go to statistical physics if our system accepts a statistical physics description, probabilistic description. So what does it mean that the system change? The dimension, grow in time, means that the number of states of the system grow in time. What does it mean that the complexity grows? It means that the entropy of the system grows in time. And that there is no upper bound for the complexity if the system is big enough. And what does it mean that it's not random or ordered? It means that, as the same assumption we did by the homograph complexity, considering that log n is the maximum entropy, or the entropy depicting a completely random system, then we consider that there is a corrective parameter mu, which can be any value inside the open interval 0, 1, which can account for the value of the entropy. So what we did now is to go to a more, down-to-earth notation, the absolute considerations we made in the beginning. So intuitively, what we have is something which is not something perfectly ordered growing in time, which is not a collection of random events which are added in time, but something which is growing in between these two extreme cases. So it's more interesting than this case and this case. What we don't have, oh my god, well, there is a box here. So imagine that we have the same box here, so it's like a Maxwell-Boltzmann system. If we open the door of this box, then particles will flow in that direction until more or less the same number of particles will be here and here. If we add another box here, which for unknown reasons it doesn't appear, then the process will be the same. The particles will flow to the right until more or less the same number of particles can be found in every box. So we don't have this kind of systems, which is the classical picture of statistical mechanics. So if we don't have this kind of system, and we are not working with holonomic constraints typical of max-n methods, can we work with max-n methods? I put the picture of Boltzmann because I think that the intuitions of Boltzmann were amazing. And I used to think that what should, if Boltzmann were alive, he would have very interesting opinions in many aspects when we are trying to work in statistical mechanics, in the kind of problems that he didn't work. So, what we have is something that, when we open the box, then not the same number of particles flow to the right, but some unbalanced situation is stabilized. If we add another box here, the same happens. Of course, there is a small number of balls going to the right, but the number of balls that we can find in every box is not constant. There is an asymmetry. So what we have is a system growing, but it has some internal tension between order and disorder that prevent it to freeze in ordered state and prevent it to reach the maximum disordered state. So what it means is that the system never reached the maximum entropy. Okay, now what we have now is a mathematical picture of the three first ansatz we have to characterize our systems, and now we are going to talk about the fourth feature that we assume to hold for the kind of systems we are studying. So, rough definition of evolution, or something that's evolving, could be a growth in time, and has some kind of inheritance, which means that the future is partially determined by the past. So, it means that there is path dependency. Without this partially, what we will have is something which is not evolving. Because if the past determines completely the future, there is no possibility of the emergence, for the emergence of innovation. So, following this intuition, what we do is to introduce path dependency through a variational principle, which means that the differences between the past and the future must be minimal. Of course, we have differences because the complexity of the system grows, so something will change. But assuming that something will change, we want these differences to be minimal. So again, we have this problem of the boxes. So imagine here that we have two boxes with different number of balls. Here we have more balls than here, okay? And then we add another box and we open this one, yeah? Then some balls will flow to the right, but since we are in a system which is rejecting entropy, then some asymmetries between how crowded are the boxes will survive. What we say is that the difference between these states and these two states must be minimal in this statistical description. However, we have to respect that complexity increases, so something will change. How can we introduce this difference? So, there is a very nice function, which is the Kullback-Leibler divergence, to account for the divergence between two statistical descriptions. The Kullback-Leibler divergence evaluates the minimal number of bits we need to provide to a system, which knowing the distribution Q wants to reconstruct distribution P. So if P and Q are the same distribution, we don't need any addition of bits. If there is divergence, the Kullback-Leibler divergence evaluates the minimal number of bits needed to reconstruct P from the knowledge of a code based on the distribution Q. So it's something like when a system shifts from one distribution to another, the Kullback-Leibler divergence accounts for the statistical entropy production. There is another interesting feature, is that there is a close relation between the Kullback-Leibler divergence and the entropy. So, which means that the Kullback-Leibler divergence is as important as entropy. And several things can be pointed out here, but one important thing is that we can reconstruct all equilibrium statistical mechanics not by using the James max-n principle, not by maximizing the statistical entropy, but minimizing the Kullback-Leibler divergence. And both approaches are equivalent. And here I put two excellent books which interestingly base information theory not in entropy but in the Kullback-Leibler divergence. This is, in this case, it must be, we can think that it's common that the same author which proposed the functional tries to build the theory under the function he defined. But in this case, which is, from my side, one of the best books of information theory, the authors decided to build all the formal apparatus of information theory over the Kullback-Leibler divergence. So, in our case, the minimization of this Kullback-Leibler divergence acts more or less as the minimum entropy production principle, And formally, the role of this functional is close to the role a Lagrangian has in a mechanical system. So, here is our Lagrangian and this is the Lagrangian multiplier for this constraint, which is only the normalization of probabilities. And this condition is due to the fact that the supports of the two functions, the two probability distributions that can be compared in the Kullback-Leibler divergence must be the same. And since there is no Pn n plus 1, we are forced to compare the first n members and then see what happens. So, what we have is that...
I don't understand.
Yes.
What about the normalization of the second equation?
Yes.
You sound...
If you look at this formula, this can be done only if P and Q are non-zero the same number of times. So if you have 1 0 here, you have a problem. And maybe we say that it's simply 0. So we should not have a problem. So this can be applied only if the support of P and Q is the same, which means that P and Q are non-zero in the same number of elements.
Do you have any constraint to P being larger than Q?
Sorry?
Do you have any constraint for having P larger than Q, or can be negative? D.
P larger than... No, D cannot be negative.
So P must be larger than Q.
Not in the particular case, it's not necessary. But this is a positive quantity.
This is a positive one.
My question was on this second formula.
Yeah, of course.
Sum overall the
Yes,
eyes for the second one.
of course, yeah. This means that in the Pn distribution, we have n elements. Okay? And the Pn plus 1 distribution, we have n plus 1 elements. Okay? So, we don't know the Pn plus 1 distribution, is what we are looking for, but we do know the Pn. Yeah? So, when comparing these two distributions, we have a problem. Because in this first distribution, there is an element which is unexistent. Yeah? So we cannot compare these two functions directly. What we have to do is to compare the first n elements of the Pn plus 1. And then properly normalized, of course. So it's a condition of...
So there's a normalization missing there.
Yeah. So, what we did until now is to set up the problem. Now we are going to solve the problem we set up. So, what is the statistical behavior of the system that grows in time, whose complexity grows as the system grows, which is not ordered, not random, and is subject to path dependency? So we have a system growing in complexity under order-disorder tensions and subject to path dependency. In a nutshell, what we have is to solve this equation with assuming that this is open, we can have any value of mu between 0 and 1, subject to the minimization of the successive Lagrangians we have when growing the system. So actually what we have here is an infinite number of equations. So, solving this, I will not go into the details. What we have is Zipf. So, moreover, what we have, being more rigorous, is that we can demonstrate that the solution is confined at the center of this chain of inequalities, and that as n goes to infinity, delta goes to 0, which means that the distribution will be proportional, or will be to the inverse of the ranking of the elements, which means that Zipf law is the unique solution for this problem, if the system is large enough. And what is important, related to the question you set up before, is that the value of mu has no role in the end. We solved this problem in a couple of papers. The way I presented the results is not exactly the way we wrote the papers. I mixed to provide more insight. And you can find it in the internet or by sending an email to me. Finally, we more or less solved an abstract problem. So we would like it has any application. So let us remind, in an informal way, the least effort hypothesis proposed by Zipf as the origin of the scaling behavior in human language. The speaker tendency is to use a few words. The hearer tendency is to demand a specific word for every element. So the balance of such effort would lead the linguistic code to display the scaling behavior. Okay. What we are saying, George Kingsley Zipf, is that the speaker's effort tends to focus in only one signal, all the events occurring in the world. The hearer's effort wants, for every event occurring in the world, one signal. The solution is intermediate. If we formalize this problem as an information problem, what we have is that the speaker's least effort tendency means that I don't want to provide information, so the entropy of signals will be low. Then the ability for the hearers to reconstruct what happened in the environment would be really high, and a lot of uncertainty would emerge. On the contrary, the hearer least effort tendency, formalized in terms of information theory, means that I don't want uncertainty, but then the speaker will have to work. If we balance these two opposite forces, what we have is that these two entropies must be equal. That's the cooperative solution for communication that Zipf proposed. And it implies, after some algebra, that the entropy of the signals must be equal to the entropy of the environment times a constant which is in between 1/2 and 1, which is exactly the problem we recently solved. So if a code, a complex code if you want, evolves under two opposite balance tensions between listener or coder and decoder, if you want to be more rigorous, then the emergent behaviors will be Zipf's law. I'm going to the end. So what we did is to rigorously characterize a general class of complex systems which grow under order disorder tensions, which have path dependency, and if the entropy of the system can grow unboundedly, this law is the only outcome. And the proof we provided is a proof of uniqueness. So, this is what we wanted, a fundamental model-free explanation for the emergence of Zipf's law. Finally, I will comment something on the papers and everything that can be consulted. And this talk has been based on these two papers. The main inspiration for the first one was this paper, which is a very interesting paper, very original paper. And for me, it's not difficult to read, and it's very, very, very suggestive. And this paper, published by Ramon Ferricancho and Ricard Soler, was, these two papers influenced it a lot to provide the idea how to solve the problem that we tackled in the second paper. Of course, it is very interesting to go to the original book of George Kingsley Zipf, and I strongly recommend you this review from Mark Newman if you want to have an idea of how common it is to find this kind of scaling behaviors in nature. And finally, if you want to go into more details of information theory, I recommend you this book, which is, the Bible of Common of Complexity, and this one, which is for me the best book on information theory. Which thank you very much. Well, I would like to add a guy that I forgot for the audience, which is Bernat, who's working with us also. Okay.
You say that the explanation is system-free, but the explanation of the least effort seems, to me at least, very dependent on the communication situation. I don't see what would correspond to this trade-off in the case of the growth of cities, for instance, on the scaling distribution of the income, or the scientific impact, or in many other areas we find these sort of distributions. To what extent is this least effort generalizable beyond?
No. I don't say that least effort is you can generalize least effort to the other kind of systems. What I said is that we provided an abstract demonstration that if you assume a very generic cluster of properties, then Zipf's law is the only outcome that you can find. And then what I did is to show that a specific problem, which is the least effort hypothesis provided by Zipf, can be formalized in such a way that the problem is isomorphic to the problem solved. I don't say that the least effort hypothesis is something that must be extended to the growing of cities, something like this. No. What I say is that what we developed in an abstract way has an application to communication, which is in a specific system.
But do you think you could generalize this sort of mechanism to find something corresponding in any system? Discover the sort of influences or tensions or pulls that need to reach an equilibrium or a thing by giving this
So I don't know, because what I would say yes, but I have to be honest. When doing statistical physics, people feel safe by maximizing the entropy, and they can create even strange entropies that when you maximize this entropy, then you find the desired distribution. So there is not only the Shannon entropy, you have a lot of different entropies, which if you maximize it, then you find the distribution you want. Does it mean that we are safe using the max-end principle? I don't think so, because we know what this entropy, Shannon entropy, means. But it's difficult to have to say the same when you are maximizing non-equilibrium entropies. So what I want to say, what I'm trying to defend myself, saying I don't know how to defend, not to defend, but to provide a clue on how entropy is dissipated when a city is growing. Okay, but I would advise you that this problem is also present in other kinds of in other topics of statistical mechanics. The problem in finding the sources of entropy dissipation rely in the fact that historically what statistical mechanics does is to find microscopic explanations, and then to see that the microscopic behavior relates to the macroscopic behavior. In that case, to go to microscopic behavior means that we take into account a specific mechanism of, for example, we have a multiplicative phenomena coupled to a diffusive phenomena. So it means that you have a tension between order and disorder, but you have a specific mechanism. So I think that one can find lots of mechanisms which represent something which has the tendency to reduce the entropy and something which has a tendency to increase the entropy. A general explanation why entropy is dissipated, I don't know.
So I have some problem. I mean, I think you pose a question and solve something completely different. I mean, you start with the distribution of word frequency, right? So how often a word appears in a text. Fine. And just to illustrate in the least effort mechanism, what you do is you match how many words are associated to the same object, right? But this in principle has nothing to do with the other one. Unless, and this you have to make some hypothesis about how often you are presenting an object, and you have to name it, right? So there are two things completely different. Imagine that, for example, you see a tree 10 times more often than a house, probably you are going to use tree 10 times more often than a house. So I see that these two things, somehow, they have some connection, or one week one that there is some connection, but in principle there is nothing. So what you are showing in the least effort case is that the polyseming, or the is given by a power law, for example, but not that the frequency of that word in a text will follow the same. So I think that the dynamics has nothing to do in one case.
No. Okay. This is the set of events. Events means not tree or whatever.
No, just to simplify, I was thinking tree
No.
or house, or an action or an event or whatever.
So I don't know so I assume that the distribution of events behaves correctly, which means that grows if the number of events grows.
No, but it's uniform, it's a power law, because that's
I mean, the only thing I want is that the only thing I want is that, okay, I'm very far away from, the only thing I want is that grows in time. In size. So if I have 10,000 events, it grows, and there is no upper bound. If I have it, then I am solving the same kind of problem I had before. I don't know if I explained it.
Well,
you are not convinced at all.
Well, no, I don't see the link between the two things. I mean, I think in one case is so you associate words to actions or whatever, to nouns or to whatever. So it's basically an association of a set with another set. And in the other case is how in a text you are using these words. And that depends on many things. That depends on the evidence you want to describe, that depends on how frequent they are, and many other things. So I think there are, maybe there is some relation, but no.
I would accept that maybe this is an oversimplification. This is a simplification, yes. So and now I understand the question. So you think, to understand you think that the mapping we have, or we do, between what happens in the text and what happens here is not legitimate?
No, it's not legitimate, it's not set. And you are not making the connections between the association of the words and the evidence and what happens in a text. This is what I'm saying. My trivial example is what I'm saying. For example, imagine that, I don't know, you want to describe in the book what happens in your morning, right? And you have seen 10 trees, and you are going to say, hey, I have seen the first tree, so tree is going to appear 10 times, for example, right? Did you say?
Yeah.
And if something else is happening, so that could be an easier explanation for that.
Yeah.
So the link between your model and the text is something that is not explained when I read your papers or when you are explaining that. And I think that this is, at least you should propose something, even if this is trivial. This is.
So I can understand, for example, so that's true that one morning maybe some word appears lots of times, but we are talking about a huge volume of data, you know? And if I understand you, so I would think that language is shaped in such a way that you have to satisfy distinction, okay? And then the use of language, whatever the context, should be subject to this kind of tension. So you say that there is no connection. I don't agree, because in that case it's a very abstract picture of what's going on. But then what happens is that you have a set of elements and you have a set of signals. You do. Then go ahead. If the set of elements cannot be coded in the same way everything, okay, no problem. But so I know the answer now, but I don't think it is a critical point. But it's not. It's like saying nothing. Okay.
I think that your point should be, well, I just started with just one book, but we can add as many speed checks as we want, and the result will be more or less the same.
Yeah, but I think that so you are not negating that the local image, but what you dispute is that this is the correct abstraction.
Yeah, I mean, my specific point here is that the connections between your abstraction in this competition between the hearer and the speaker is far from what I'm doing in a textbook, in a book in general. So that perhaps the connection between the words and the actions is like you are saying, but still this is not explaining what I would do in a book, unless I'm saying that the events that I see, they are uniform, or the events that I'm describing are like that, or whatever. I mean, so there is some this link is missing, and I never saw that, not to you or to Ricardo, in the paper, so I just wonder about that.
Well, I have to say that if you assume that this grows, so you solve this problem.
Okay, maybe fine. Okay. Let's stop it.
So,
Okay. Thank you very much.